Hello, and welcome to Lecture 15 on the topic of LC and especially RLC circuits. These are oscillating circuits, and this lecture truly represents the culmination of all the previous lectures where we've talked about circuits, from very early introductions of resistance and capacitance, and more recently discussing inductance. Okay, and of course, Ohm's law is going to show up here as well, because after all, we are talking about circuits. Also, this is the penultimate lecture in the entire electromagnetism section of physics, with lecture 16 culminating in electromagnetic waves. So it's an exciting point in all of this material, building up so many ideas and then applying them together. So let's get to it. So we have a few objectives here. I want us to learn the basics of an AC circuit that has a resistor, capacitor, and inductor all in series, okay? Furthermore, we want to understand how the concept of a phasor helps us understand the total voltage in an RLC circuit, as well as the total impedance, a term we'll introduce, on the current, okay? We want to understand how the concept of phasors allows us to calculate the phase angle of an RLC circuit and use that angle to find the power factor and thus the average power output of that circuit, all right? Because that's a way for us to quantify power. We're always interested in power if we're talking about circuits. We want to learn that RLC circuits have a resonant frequency that occurs when the reactance of the capacitor is equal to the reactance of the inductor, which results in a minimum total impedance and thus a maximum current, all right? And finally, we want to recognize that the resonant frequency is equal to the natural frequency of an LC circuit on its own. All right, that's really as much as we're going to talk about LC circuits. Obviously, a lot to unpack there, a lot of new key terms. So let's build on these ideas. Let's think about what we mean by these objectives. Okay, so these are going to be our phasor diagrams. I have quite a few of them here over on the right-hand side of the page. All right, so let's look at our key terms. First of all, what is a phasor and what's a phasor diagram? Okay, so a phasor is a rotating vector. It rotates with an angular frequency omega. Now remember, omega is 2 pi times frequency, all right? Okay, so I don't want us to get too worried about it being a new type of vector. It's simply just a rotation. Think unit circle. It's very similar to ideas you've seen before, I'm sure, okay? So let's take a look at our phasors, all right? This would be a phasor for current, all right? This would be a phasor for the voltage across the resistor in a circuit that has a resistor, an inductor, and a conductor, all right, a capacitor, excuse me. Here is the voltage across the capacitor, and here is the voltage across the inductor. Notice, I'm gonna zoom in on this a bit, notice that we have Ohm's law expressed for the voltage across the inductor, and we have Ohm's law expressed for the voltage across the capacitor, all right, as well as the resistor for that matter, all right? So this is all stuff we've seen before, all right? The reactance shows up, right? That's the reactance of an inductor, that's the reactance of a capacitor. Those expressions for the reactance for these two circuit elements will certainly come up in this lecture, but I'll remind you what they are. But they were introduced first in lecture 14, okay? All right, so let's think about then the idea that it rotates, because we see, I show that, and it's shown in this diagram immediately below, because these are all the same vectors, right, for the voltage vectors and the one current vector, but they have rotated because we've let the process, this oscillating circuit, proceed through its natural oscillation, okay? And so the vectors have rotated as time has passed, right? Because omega t represents phi, the angular displacement of the phasors, okay? All right, add some labels, okay? So we're defining positive theta in terms of positive theta displacements as being in the counterclockwise direction, which is typical, all right? And that's why the phasors are by default rotating in the counterclockwise direction, all right? And here I show the phase angles, the phase shifts, of which we already introduced in lecture 14. Again, review lecture 14, the fundamental phase shifts between the input current from the AC source and the different circuit elements, okay? And that, such as the voltage across the inductor is pi over 2 radians ahead of the input voltage. The voltage of the resistor is in phase with the current, all right? And the voltage of the capacitor is pi over 2 radians behind the current, okay? So the inductor leads the current by pi over 2, the capacitor lags behind the current by pi over 2. Both pi over 2s representing a quarter of a period, okay? Because there's 2 pi radians in a period. 2 pi rads per oscillation, okay, per period, however you want to say it. Okay, all right. So let's then think about a very helpful way of interpreting this rotating phasor diagram. It's just a cosine curve. At least it is for I, or maybe it could be sine, right? Because for a different quantity. But if we think of the input current, well, the input current over time is going to be following a sinusoidal behavior. So that's just current as a function of time. And that's going to show up in the phasor diagram, okay? Now, how so? Because you might say, well, this vector always has the same length. So how is this vector then going to, say, pass through a quantity of 0? All right? Because of projections. Really, this is no different than the idea that uniform circular motion and simple harmonic motion are mathematically equivalent. It's basically we're going to project onto the x-axis. That represents the value of instantaneous current, okay? So that's what this is all about. But before I define that and before I put that in the writing, I just wanted to appreciate that phasors are just a way of representing sinusoidal behavior, okay? A function that is sinusoidal, okay? So a phasor diagram represents the phasors on an XY graph, as we were just talking about, and shows the instantaneous values of current and voltage as projections on the x-axis, okay? That's how we actually represent them. The instantaneous values are projections on the x-axis. Let's show this in diagram C down below, right? So all we're doing with these diagrams is I showed the basic phasors for an RLC circuit. These are the only phasors that we'll discuss, okay? The one current phasor and then the 3 voltage phasors. Then we rotated them because we let time pass, just a arbitrary choice of letting it rotate about 45 degrees, all right? Or pi over 4 radians. And now we're going to talk about those projections, right? So that's all that's different about down here is I'm just showing the projections of the voltage across the inductor, the voltage across the resistor, the voltage across the capacitor, and the voltage across the resistor, as well as the current from the source, all those projections onto the x-axis. And that's what the dotted lines are here, okay? All right, excellent. So let's go ahead and label those, all right? So notice the instantaneous current, all right? So the instantaneous current is the projection of the input current onto the x-axis. The instantaneous current would show up on our cosine curve as just being the value at some point t, all right? The same t that shows up here in the omega t, okay? Because notice, as the current rotates all the way up until it's, say, parallel with the y-axis, the current approaches 0 and indeed will have an instantaneous value of 0 after a quarter period occurs, right? And then this is just showing the relationship between period along the axis as measured in time and the angular frequency, because period is equal to 2 pi divided by the angular frequency. Okay, all right? And then all the other x components that I mentioned, right, represent the instantaneous values for the other phasor quantities. All right, there, right? Projections on the x-axis. Okay, continuing on with our key terms, impedance. Okay, so impedance isn't going to show up on this page in terms of a diagram. I'll show it on the next page, but impedance represents the overall effect of the reactance and the resistance, okay? Impedance is the total effect of reactances and resistances on an RLC circuit's current, okay? So it's how much the overall current is impeded, slowed down, okay? Impedance has units of ohms. I'll repeat that a few times, all right? Note, resistance, reactance, and impedance all have the same units, all right? Okay, because they can all be used with Ohm's law, that proportionality between voltage and current. Okay, moving on to our next term, the phase angle. Okay, so what phase angle? Seems like there's a lot of angles. This is the angle that I talked about that was just omega times t. No, it's a very specific angle, all right? It is the angle of a right triangle formed by the difference between the voltage across the inductor and the capacitor compared to, and the other side of the triangle is the voltage across the resistor. All right, so we've got 2 legs of the right triangle. One is the difference between those 2 voltages, and one is just the voltage across the resistor. Okay, and you'll see naturally why we group them together. And it's defined as cosine of that angle phi, okay, because the phase angle is defined as phi, as being the ratio of the voltage across the resistor over the overall voltage, the total voltage, or we can define it as sine with this difference over the overall voltage, or even as tangent of the phase angle, in which case the overall voltage doesn't show up because the overall voltage of the RLC circuit, of course, is the hypotenuse of the right triangle that I'm mentioning. Okay? All right, so let's go ahead and show that. Okay? Oh, I have one other point to make. The phase angle is determined by the material properties of the resistor, the inductor, and the capacitor, and the frequency of the AC current, okay, the external current you're putting in. And that's because these terms are all dependent on those quantities, right? Because you think about inductance is determined by the number of coils and the diameter, capacitance is determined by the plate area and the separation distance and whether there's a dielectric, resistance is just determined by the length of the wire and the diameter of the wire, and reactance of capacitors and inductors also are, well, they're frequency dependent. So that's everything that goes in. And if you know all that, then you know your impedance, you know the overall effect on the current, and thus you know the phase angle, okay, and the power, okay. So here is the phase angle shown up in our continually evolving phasor diagram. So what change have we made from part C down to this last version of the phasor diagram? Well, what we've done is combined the voltages, right? Because notice before we had the voltage across the capacitor and the voltage across the inductor shown separately, which makes sense. But look, they're along a single axis. So it makes sense to consider the difference between the two and thus have a single phasor, because now that phasor naturally forms the aforementioned right triangle with the phasor for the voltage across the resistor. And that gives us the total voltage across the RLC circuit. Okay, all right, and there is that phase angle. Zoom back out of it. All right, and also notice that as we can project anything onto the x-axis, we can project the total voltage onto the x-axis to get the instantaneous total voltage. All right, and then as I mentioned, the difference is just the combined voltage across the inductor and capacitor. Okay, and because they're exactly half a period out of phase, which is why you just take the difference. It's like an arithmetic effect because of those particular vectors. All right, so last term here, power factor. It is defined as cosine of phi. Okay, so it's this one. And its value affects the average power output of the circuit. I'm not going to derive where it comes from, but we're going to see when we talk about the power output of an RLC circuit that that power factor cosine of phi is right there in the formula. Okay, let's move on almost to formulas, with one last term, an LC circuit. All right, so what is an LC circuit? We won't talk about it much. I'm not going to do any example problems with LC circuits, but it's important to understand what it is and how it relates to an RLC circuit. So an LC circuit is the part of an RLC circuit that sets its natural frequency. Okay, so it's much more simple than an RLC circuit. There's no source of EMF. There's no AC source. There's just an inductor and a capacitor. Notice also there's no resistor. Okay, so this is just a perfect oscillator. No slowing down, no loss of energy. The energy is just going to oscillate back and forth. It's going to slosh back and forth between the inductor and the capacitor. Okay, so the RLC circuit is a driven damped oscillator. All right, that's a term for this type of process. That also is a term that shows up in mechanics. Perhaps you've seen it or recall seeing it in the mechanics part of physics. Okay, the LC circuit, okay, that kind of the heart of the RLC circuit, is the simplification to a simple harmonic oscillator. It is like just a single mass in a spring, the most ideal simple harmonic oscillator there is. Okay, like a mass attached to a spring, the current and energy of an LC circuit will oscillate back and forth, transforming potential energy in the capacitor, right, when all the charge gets stored on the plates, to potential energy in the inductor, when there's a strong current running through the inductor and there's stored energy in the magnetic field. All right, so it's transferring energy back and forth from one form to another, just like the mass and spring transfer energy from elastic potential energy in the spring to kinetic energy of the mass, back and forth, back and forth. All right, and if we think about that energy transfer, then we can color code the inductor and its energy as green and the capacitor as pink. And take a look at this graph, which just shows the total energy in the system is unchanging. So the total energy remains constant. There's no loss of energy to, say, heat. And we just have an oscillation between the potential energy of the capacitor, expressed here as a good choice of being 1/2 the capacitance times the voltage across the capacitor squared, right? One of the ways that to express potential energy stored in the capacitor. And then the potential energy stored in the inductor, and the only way that we've seen it, as 1/2 L times I squared. All right? It's just oscillate back and forth. At some point, it's all in the inductor, none in the capacitor. Sometimes it's a mix between the two. Okay? That's the system. That's the perfect oscillator, which is an LC circuit. Okay? So finally, on to our key equations with one other diagram to put all the key equations into context. Now, this diagram absolutely is a phasor diagram, isn't it? Right? These are all phasors here shown on the XY axis. This one is here. But then I take the phasors and I just then treat them as triangles, just to call attention to the trigonometric, fact that we're dealing with right triangles here, and using, SOHCAHTOA, sine opposite over hypotenuse and so on, just to define our quantities. Okay. And notice that the total impedance, term introduced on the previous page, is represented by the letter Z. It's measured in ohms, right? And it's the impedance of the RLC circuit. Okay, all right, on to our key equations. Okay, so the first one is the maximum voltage across the RLC circuit. Okay, and it is equal to, well, the Pythagorean theorem of the voltage across the different circuit elements. Why do we know that? We know that from the phasor diagram. We know it from what we were just talking about the previous page and showing right there, okay? This is the right triangle formed by the voltage across the circuit as a whole and the voltage across the elements, all right? Okay, all right, now the impedance is our next term, okay? This is impedance of the RLC circuit, Z, and it's equal, also with the Pythagorean theorem, to this expression, okay? Again, just the sides of the triangle, all right? All right, and we see that it's this triangle right here. Now this begs the question, how do we go from a triangle that has voltages to a triangle that just has values of impedance, resistance, and reactance? Well, that's because the difference between all of these, the connection between all of these is Ohm's law, and the current is shared by every circuit element because it is, after all, a series circuit. So current cancels out, and thus these two triangles are similar triangles, which is to say equivalent angled triangles, okay? So mathematically it holds, all right? Now we can see from the triangle that we now have our definition for the phase angle makes good sense as being opposite over adjacent, where the opposite side of the triangle is the difference between the voltage across the inductor and the capacitor, and then the adjacent side is the voltage across the resistor, which is this one here actually, okay? But then as I said, since they're similar triangles, we can also express the tangent of the phase angle as the ratio of the difference between the reactance across the inductor and reactance across the capacitor, all divided by the resistance, okay? All right, and this is a reminder of what reactance looks like for the inductor and the capacitor, okay? Previous lectures formulas, but they come up quite a bit here, so I wanted to call attention to them. And again, we see the relationship between frequency and how, frequency has an inverse relationship on reactance for capacitors and direct relationship on reactance for inductors, okay? All right. Furthermore, just calling attention to, as I mentioned before, we can say that this is a true statement because the current cancels from the equation. All right. Then we've got Ohm's law. All right. Oh, that's a phase angle, as I mentioned. Okay. Oh, one more thing. Note that when the phase angle equals 0 degrees, that happens when the reactance of the inductor equals the reactance of the capacitor, which we can see, right? Because if I set these two reactances equal to each other, then my numerator up here would just go to 0. And the only way for that to be true is for the angle to be 0, because tangent of 0 degrees is 0, okay? All right. So then, as I was saying a moment ago, we have Ohm's law expressed for our RLC circuit, okay? So we've seen Ohm's law way back for a basic circuit with just a resistor. We've seen Ohm's law for alternating current circuits that just have a single inductor or a single capacitor, but now we're seeing it for an RLC circuit, okay? And we just see the version with maximum voltage and the version with the root mean square voltage and current, okay? All right, so kind of depending on how you want to use it, you can use it either way. All right, now the average power, okay? This is the average power for our RLC circuit, average power output of the circuit, okay? So we can express it in terms of the root mean square voltage. So basically, this would be just traditional power, right? Power is just I times V, okay? But here we have the power factor, because depending on the phase angle, we either get less or more average power, okay? And then we could also rewrite this as 1/2 times the maximum voltage and maximum current. And you might wonder, where does that 1/2 come from? Well, it just comes from the fact that IRMS equals Imax over root 2, and likewise for VRMS. So then we have a root 2 times a root 2. Well, the square root of 2 squared is just 2. So that's where the 2 comes from. Okay? All right. And there's the power factor, cosine of phi, the one that's mentioned in the key terms. Note that average power is maximum when cosine of phi equals 1, which happens when phi equals 0 degrees. Phi equals 0 degrees. We saw it just a second ago, right? When the reactances are equal to each other. Okay? And finally, we have the resonant frequency, which is the max power output. Okay? This is, you get max power output when you achieve the resonant frequency. Okay? So the resonant frequency would be the frequency from the AC source. Okay? So it could be adjusted by the AC source, and it's dependent on the properties of the circuit. Specifically, it's dependent on the inductance of the inductor and the capacitance of the capacitor, which of course then is based on their physical parameters. Notice that the resistance of the resistor does not show up in the resonant frequency calculation. The resonant frequency is independent of the resistance. The resistance just defines the damping in the circuit. It doesn't actually define its oscillation. Okay, and this expression right here is simply derived from setting the two reactances equal to each other. Because when the reactances are equal to each other, we get max power. Well, max power is resonance. That's what resonance is. Resonance is getting the most out of your circuit. If you're getting maximum power, that's because it's resonating. Resonating is a physical phenomenon, not just for circuits, of getting the maximum effect for input. Okay? So, in other words, we keep coming back to this idea of setting the reactances equal to each other at a phase angle of 0 degrees to get the maximum state for the circuit, for the RLC circuit. Okay, so a lot of ideas. Let's do our practice problems, okay? Now the practice problems are not as complex as the ideas themselves. The actual approach to solving these problems is fairly straightforward, I would say, and there's only one type of problem, just problems that involve an RLC circuit and the formulas that we were just covering. Okay, so example 1. What is the impedance of the shown circuit? Okay, well, it's an RLC series circuit. It's the only type of circuit we're talking about in this lecture, really, other than qualitatively talking about LC circuits, right? It's the only type of circuit we're talking about quantitatively, right? We have a source, right, with a certain frequency and a RMS value of voltage, right? This is an AC source. Okay, all right. So we want to find the total impedance. So that means we need to find the reactances of the inductor and the capacitor. Okay. So let's collect what we know. We already obviously know the resistance. All right. The reactance of the inductor is just 2 pi FL, which ends up being 63 ohms. Okay. The reactance of the capacitor is the reciprocal of 2 pi FC. And plug in our values. All right. Because they're all specified here in the diagram. And we get 21 ohms. Excellent. So then we can find the total impedance by just plugging in the values. All right, see, let's take the difference between 63 and 21, squared that, all right, squared the 50, put it all inside the square root because of the Pythagorean theorem, and I get 65 ohms as the total impedance of the circuit. Now, I'm always in the habit of saying total impedance. It's really just the impedance of the circuit. I think of it as a total because we have to consider everything else to get there, right? But it's the impedance of the RLC circuit. Okay, and then part B, what is the RMS current through the circuit? Okay, well, now we're just going to use this value in Ohm's law, all right? So here we just rewrote Ohm's law to solve for the RMS current and plug in what we know. So we know the RMS voltage is 240 volts divided by the impedance that we solve for in part A, and we get 3.7 amps. Excellent. Okay. All right, onward to example 2. A 58 ohm resistor, a 0.4 Henry inductor, and a 10 microfarad capacitor are connected in series to a 160 hertz source. The RMS current in the circuit is 3.99 amps. What is the phase angle of this circuit? Okay, so we certainly could have solved for the phase angle in the previous example. We weren't asked for it. So this is very similar in example 2, just to ask for slightly different information and being given the RMS voltage, or rather current instead of voltage. Okay. All right, so let's go ahead and find the impedance based on what we were told. All right, so we're just plugging in the values here. Notice that I had to kind of combine everything in here, right? So instead of solving for the reactance as a first step, I just combined it within the formula. and we get an impedance of 130 ohms, okay? And now we're going to go ahead and use the phase angle formula that says that tangent of phi is this expression here. And then we're just going to go ahead and solve for phi, all right? So here I'm just combining everything, okay? And I kind of did this in a not very straightforward way, right? Because I didn't, I found reactance, right, obviously, and then plugged it in here, but I don't show that calculation. So there's kind of some back and forth work, but regardless, here we have the reactance of the inductor and the reactance of the capacitor. All right, and we're just taking tangent inverse of that ratio. And that gives us a phase angle of 77 degrees. Excellent. Okay. And then what is the average power dissipated by the circuit? Okay. So let's go ahead and put some of these values to use. Okay. So the average power is going to be the IRMS and then the VRMS times cosine of the phase angle. Okay. And I went ahead and found this 518 volts by just taking the known 3.99 amps and dividing by, or rather multiplying by the 130 ohm impedance, okay? So yeah, that's where this value comes from, and that's really why I solved for the impedance so that I could calculate the VRMS, okay? And so then finally our average power is 464 watts. Okay, and again, we use the impedance to find the voltage because voltage, RMS, is just IRMS times impedance. V equals IR, okay? But here, R is replaced by impedance, Z. Okay, all right, let's take a look at a concept question. In an RLC series circuit, the source voltage is leading the current at a given frequency F. If F is lowered slightly, then will the circuit impedance increase or decrease? All right, now this is really interesting. How does the frequency affect the actual impedance? Well, let's see. All right, so here's our expression. So notice that as the frequency goes down, we have that the reactance of the inductor goes down. As the frequency goes down, the reactance of the capacitor goes up. Interesting. All right, so that means that these two numbers are going to come closer together. Well, thus, the difference between them becomes smaller. All right, and therefore the impedance decreases. All right, so as the frequency decreases, the impedance decreases. Very interesting, isn't it? Okay, all right. So let's do another example. This one is the epitome of a plug and chug problem. An AC series circuit contains a resistor of 30 ohms, a capacitor of 1.22 microfarads, and an inductor of 154 millihenries. What frequency should be used to create a resonance condition in the circuit? Well, we got our formula for resonance, and we have everything we need to plug in, right? And we just plug it in, right? Plug in the value of the inductance, plug in the value of the capacitance, acknowledge that it's milli and micro, so we have 10 to the negative 9, and we get 367 hertz. Also, note that the resonant frequency is independent of the resistance, and this frequency matches the natural frequency of an LC circuit made with the same inductor and capacitor. Okay, so if we just took the inductor and capacitor, took them out of the RLC circuit and connected them to each other, as long as the capacitor started charged, they would just oscillate back and forth at this frequency. Okay, forever if there's no resistance in the wire or any other device. Okay, all right. So here's an interesting concept question. LC circuits have a mechanical analog and masses attached to springs, as I mentioned before. In this analogy, does the capacitor behave more like the spring or the mass? And what about the inductor? Okay, so we definitely said it holds that same idea of transforming energy back and forth, but is there a clear case of which is which, Well, there is, okay? The capacitor is like the spring. Storing the energy as a restoring force grows in magnitude. The restoring force is the repulsive force between the like charges. Because if you think of the plates of the capacitor, they build up like charges. Those like charges don't want to be close to each other. And then they eventually, as they get closer and closer packed together, reach a maximum state for the physical parameters of the system and then push back. Okay, so that means the inductor must be like the mass. That seems like kind of a stretch, isn't it? Well, not really. The inductor is like the mass, possessing inertia and assuring that the current continues to flow each time the charges are in a force equilibrium. Because that's what the mass does. Because you think what happens when the spring returns to its equilibrium state, instead of just returning to rest, it continues in motion because there's 1/2 mv squared, and that m means that the mass has inertia, and it wants to keep moving. It doesn't just stop at the equilibrium point of the spring, okay? Likewise here, because there would be some distribution of charges throughout the entire LC circuit, where all the electrons are the appropriate, basically their maximum distance apart. That would just be how the circuit would be at rest, but it doesn't get to that state because the inductor, due to the fact that it responds to changes in current due to Faraday and Lenz's law, effectively acts like inertia and continues pushing the current, okay? Right through the equilibrium point. Okay, now let's do our final example. An LRC series circuit consists of a 1.5 microfarad capacitor, a 6 millihenry inductor, and a 71 ohm resistor that are connected across an AC voltage supply with a maximum voltage of 13 volts. What is the RMS current through this circuit if the average power is 5/9 of the RMS value of voltage times the RMS value of current? Okay, how do we go about this? Well, first we find the phase angle. Okay, by definition, average power is VRMS IRMS times cosine of phi. And in this particular case, we know that the average power is 5/9 times the product of RMS voltage and current. Therefore, we can set the two expressions for average power equal to each other, cancel out the RMS of voltage and current, and just get that cosine of phi is equal to 5/9. Therefore, if we do an inverse cosine, we can find phi and find out that in degrees it is 56.3. Okay, excellent. We've got our phase angle. Now, what do we do with that phase angle? We use the phase angle to find the angular frequency because we're not given the angular frequency of this circuit. And we certainly need the angular frequency if we're going to find impedance. Okay, so then we take basically the right triangle formed from our phasors and all the aforementioned definitions, and we're going to use that, set it up like this, right? This is one of our key formulas, and use it to find omega, the angular frequency. Now we could just as easily find f, but then we'd have an extra 2 pi to deal with. So I'm just going to find omega, the angular frequency, because remember again that omega is just equal to 2 pi times the frequency. Okay? All right. So how do I go about doing that? Because my unknown in this equation is omega. I know everything else, don't I? I know phi, so therefore I know tangent of phi. I know the capacitance, I know the inductance, and I know the resistance. Okay? Well, got to isolate omega. So I cross multiply by r, and then I look, okay, so how am I going to do that? Well, now I'm going to multiply each term by omega. So then my expression becomes this. Well, I have myself a quadratic equation, so I need to use a quadratic formula to solve my unknown. Essentially, this is my x, right? Okay, so I set this up and I plug in my values, right? Because I have negative b plus or minus the square root of b squared minus 4ac all over 2a, all right? Only the positive value makes sense here because otherwise we can see that we would have a negative angular frequency. A negative angular frequency would make no sense in the context of this problem. And so then only the positive offers a physical solution, or a solution that makes physical sense. Okay? All right, and now I'm just going to plug in all my values into my expression here for the quadratic formula. And when I do that, I get an angular frequency of very large of 2.26 times 10 to the 4 radians per second. The reason it's large is because our values of inductance and capacitance are small. That's gonna drive the frequency up. And furthermore, this is the angular frequency, which is always about 6 times bigger than the frequency. But it's still a very fast oscillating circuit, which is typical of circuit elements where the capacitance and the inductance aren't exceptionally large, because typical capacitors and inductors are small. So you can think of this as a reasonable value, kind of a typical value. Okay? All right, so now what do we do with that angular frequency? Well, now we take that angular frequency and we put it into the expression for impedance, okay? Because now we have everything we need in order to solve for impedance, okay? So now I can find the impedance Z, okay? So I plug that in because I know that the reactance of the inductor is just omega L, and I know that the reactance of the capacitor is just the reciprocal of omega C. Okay, so there's the 1 over part. Okay, make sure to square the terms within the Pythagorean theorem, and I get a impedance of 128 ohms. Finally, I'm going to use that impedance in Ohm's law to find the RMS current, which is what we were asked for. We were asked for the RMS current through the circuit. Okay, so let's go over to Ohm's law, and the RMS current is just the RMS voltage divided by the impedance. I was given the maximum voltage, so I'm going to divide the maximum voltage by root 2, which gives me the RMS voltage, divide by that impedance I solved for, and there we go, we get 71.9 milliamps. Excellent. Okay, well, I hope this lecture introducing RLC circuits, and as I said, being a culmination of so many ideas, has been interesting and informative, and I also hope you feel relieved and excited to have gotten through so many electromagnetic topics. Thank you so much for watching.